We are talking about derivatives and the chain rule today. Look at the definition of f being differentiable at a point, A. That is a function from some domain into some space. So f is differentiable at a point if there exists a linear operator that I'm calling L, such that this limit here, as h goes to 0, and in the numerator we have the difference between the function at a plus some displacement h minus the function at a. So this gives you the difference between f at a and f at some point close to a. And we want this difference to be approximated well by a linear operator. So the difference between the true difference in the value of the function minus the linear approximation, so L at A, will act on H. So this will be your linear approximation to the change in the value of the function, all divided by the magnitude of H. This limit has to be 0. So if you wanted to find the derivative of some function, you could try to extract the linear part. So to find, this is one way to approach some problems, to find a derivative, right, of a function, and actually show that it is a derivative, that the function is differentiable. We can try to maybe extract the linear part of f at a plus h minus f at a. It's linear on the vector h. Well, on h. I just say on h. And that maybe that's the linear, the part of this difference that acts on h in a linear fashion. Maybe that is our linear operator, which is our derivative. So number 2, maybe then you want to show that indeed that linear part, let's just call this L, satisfies the definition, the limit definition. So I'm going to use a non-obvious example, right? Here we're going to have a matrix equation. It doesn't matter, say f of x is some power of x, let's say x cubed. So if I wanted to try to see if this function is differentiable at some point. So x is a matrix, right? It's a square matrix, so it's a set of m by n. Well, let's just say n by n matrices over the real numbers. Say such a matrix might represent a linear operator. So x, you can think of it as representing a linear operator from Rn into Rn. Well, it is a linear operator, right? So anyway, but this is a matrix function. And so if somebody says, well, what's the derivative of this matrix function? Well, we can try to do, let's see if we can get a linear operator on h, right? So let's look at the function at some matrix x plus some matrix h representing the perturbations from the entries of x, right? Minus the function at x. So our linear operator is to approximate this difference. So we're going to have x plus h cubed plus x cubed, or minus, sorry. Right, so notice that this is not unlike, kind of like what we, if we just had a real valued function from R to R here, and we look at the definition, one variable definition of derivative. H is a number here. The idea is that we kind of saw that there's, if you look at this difference, a lot of stuff canceled out. Let's just look at that. So I'm going to cube the two terms in the parentheses. Subtract x cubed. Notice that this part goes out. And then if I look at this expression, what term here is acting on h in a linear fashion? Well, you can't square or cube h, right? Because that's not linear. h1 plus h2, say, cubed is not the same thing as h1 cubed plus h2 cubed. So it's not a linear thing. So this over here is the only linear term that acting on h, right? So because it's a simple multiplication of h is a linear thing. So my guess would be that, okay, this is the linear part of this difference. So I would guess that if there's a derivative, it would be 3x squared, right? Which it is. And then you might want to say that this derivative acts on h by simply multiplying it. So this derivative acts on h. So here, I want to, in this example of this matrix function, let's do the same thing. But just we have to keep in mind that matrix multiplication is not commutative, unlike scalar number multiplication, yeah? X is multiplying h from the from the left. Now, this time around, h is multiplying x from the left. And x times h is not necessarily the same as h times x, right? It's not true. Those are not equal in general. Plus h times h. So this time here, x is going to multiply this term from the right. So it's going to be x, h, x. Okay, so we expanded this, and now we're going to look for, well, we're going to look for any cancellations. X cubed cancels, x cubed minus x cubed is 0. Okay. So now we look for the terms that act in a linear fashion on h. So basically it's going to be any terms that just have a single h in them, because it's all matrix multiplication, so that's linear. So the only thing it would be nonlinear if you're squaring h or raising h to a high, some integer power greater than 1. So this is not linear in h. Again, because h plus g, say, a matrix squared is not the same thing. This is linear in h. This is not linear, and maybe you can try to see why that is. H plus g times x times h plus g. So here I'm going to let x multiply h from the right. Likewise g. Okay. So that is not the same as hx h. And then gx g. Okay. So that's not linear, and obviously neither is the cubed. So if I had a candidate or linear approximation to the difference of f at x plus h and fx, then I would just choose this linear operator acts on h, right? It's not enough to say that this derivative is going to multiply h. It multiplies h in a way we're not used to, I guess. So that would be our derivative. That's our candidate for the derivative of this matrix equation, this x cubed at x acting on h. Okay, so number 2, maybe once we have this candidate for our derivative, maybe we can use the limit definition. And here, h is a square matrix, so we're just going to use a matrix norm of some sort. So h goes to 0 matrix. Okay. We have the function of x plus h minus the function of x. We already did that. And then we have minus the linear operator acting on h. divide that by, I guess we can just take the norm because the upstairs is a matrix, so norm, divide by the norm of H. And that's terrible. And take a limit. We're going to show that this limit is 0. All right. All right, so that this we already computed, and I'm just going to write it out. So all that is just this part. And then minus the linear operator acting on H, and we think we have a good candidate. Okay. All divided, so that's, I already distributed the negatives, so I apologize for that. All right, so we have lots of nice cancellations in the numerator, kind of like what we saw in first semester calculus. So let's see, x cubed minus x cubed. Notice the linear part on H here will cancel, those will cancel out. The xhx cancels, it's negative there. Hx squared cancels with minus hx squared. And then x squared h cancels with x squared h. So I'm just going to write down the remaining terms. All right. So now we notice that H is a common matrix factor in all 4 terms that are left in the numerator. So we can just factor that out, let's say to the left. Oh, no, we can't to the left. So this is a norm. So we have sort of triangle inequality, right? So we can maybe just use the fact that the norm of A plus B is less than norm of A plus norm of B. By the defining properties of what a norm is. Okay. So what we can do, if I put equality here, now I can say that this should be less than or equal to, and we apply this triangle inequality to the numerator. Okay, so now you might use the property that the norm of A times B is the same as norm of A times norm of B. I guess we can also use that for the H squared. I kind of cheated over here. So now we can take out a factor of magnitude of H from the numerator in anticipation that it'll cancel the factor in the denominator. Because now we're just multiplying numbers or magnitudes, right? So that's just a commutative number multiplication. Those H magnitude of the norm of H divided by norm of H is 1. And so now we're ready to finally compute this limit. We know the norm of 0 matrix is 0, so as H approaches 0, the norm of H also approaches 0. Well, I guess there's 3 of them now. We can simply lump these like terms. So indeed, H goes to 0, its norm goes to 0 as well. So we get 0. Okay, so the definition is satisfied. At the end of the day, this limit turned out to be 0. So indeed, our linear operator here satisfies the definition of derivative. So our derivative can be thought of as that function on H. Okay, now this is not the only way, right? We extracted a linear part from some function as a which gave us a candidate for the derivative. And then we use the limit definition to show that indeed it is. There are other methods I could show you later. I think your professor might even prefer. Okay, so we'll now do a more an example with a function that's more familiar to us. We're going to look at a function whose domain is all of R3, as it turns out. And this function returns a real number. So what's the derivative of this function? Is this function differentiable everywhere? Well, here we know that if a function is differentiable, it's for a function from Rn into Rm. So that's just a theorem that I'm going to read. It should be technically an open subset of Rn, but whatever. I'm just trying to indicate that the inputs have 9 coordinates. That the derivative of this function at a point is, if this function is differentiable at that point, it's just a m by n matrix, the Jacobi matrix of partial derivatives. So you differentiate the first component of f with respect to the first component of f with respect to the next coordinate. Finally, the derivative of the partial derivative of the first coordinate of f with respect to the last coordinate. And then you take the next coordinate. Well, just to be clear, f returns a vector in Rm, so it has m components. And all these components are functions of the input x. So that we then repeat, for the second row of our Jacobi matrix, we differentiate the second component of our function with respect to the n spatial coordinates. Or sorry, the n coordinates. And we keep doing this until we get to the nth component of function f and differentiate it with respect to the, right? So essentially the rows are gradients of these component functions. So if you'd like, the Jacobi matrix at x is just you have the gradient of the first component, and the next row is the gradient of the second component, and then all the way through the nth component. So there are m rows, but the grid, we have n coordinates, so it's going to be an m by n matrix. Now, also recall that I said that if f is differentiable at a point, then the derivative is the Jacobi matrix. And we also have sufficient conditions for differentiability for our function from Rn to Rm. Again, this is just a review of one of the theorems. So if the partial derivatives are, well, first order partial derivatives, I should say, these partials exist and are continuous, then f is differentiable. Now it's possible that the converse doesn't hold, right? In general, you can look at an example of a function which is differentiable at a point, and the partial derivatives exist, but they're not necessarily continuous, right? So differentiability, as we say, right, implies continuity of the original function, but differentiability does not imply the continuity of the partial derivatives. All right. So here, a good candidate, of course, is just the Jacobi matrix here. So this is a function from R3 to R, so it's just really it's like the gradient of be transposed. So my candidate here would be, all right, the derivative of f with respect to x for the first component. This is a 1/3 matrix. All right, so then the derivative of f with respect to y, and then the derivative of f with respect to z. All right, so then is it truly a derivative? This derivative has to act in the linear fashion on R3, right, and return a vector and, a number. So if we represent our vectors in R3 as column vectors, so H would be a 3x1 matrix, if you will, then DF must somehow act on this. And DF, our candidate at least, is 1x3, so that we get a number. So a 1x1 thing, right? Just a number. So it looks like you can think of DF as either, as matrices, it's just a multiplication, right? Multiply a 1x3 matrix with a 3x1 matrix, you get a 1x1 matrix, i.e. a number. We can also think of it as a dot product if you want to think of these as gradient then. Okay. That would be equivalent, right? Same thing. So I'll draw it out here just to be sure it's clear. So we think the derivative is this Jacobi matrix, so it's the derivative with respect to x, y, and z. And it should multiply a vector in R3. We represent these as columns then. That would be it. We see that this is the same thing as the dot product here of the gradient with vector h. So now, since we think this is a correct derivative, let's just use the definition, limit definition to confirm. So limit as h, a vector goes to 0. Here we're going to have, yeah. So I guess I'm thinking I better write this as x, just to emphasize that this is the position vector, the coordinate vector x. Probably not the best notation. So here we think that this differential operator at x should act on h by simply multiplying it from the left. We're going to try to prove that this limit is 0. So let's go ahead and write this out. All vectors. This is just this. So now we think we have our linear operator. Let's just write this out, right? This would be, so when you multiply that out, you get 2xy times h1, x squared times h2, 3z squared h3. Okay, and then the norm of h there is just the square root, regular old norm, Euclidean norm. So this part is here. Let's multiply the business out and do some canceling. See you in a while. So after distributing the negative inside the parentheses. All right, I multiplied it all out. So it looks like we're going to have some cancellations. So the function part actually cancels, right? Z cubed minus z cubed. And that's all I see there. But what you want to, maybe what we want to notice is that the stuff that's in green, our linear operator acting on vector h, you see that over in this this expansion, the yellow, right? We have 2xy h1 over here, and then x squared h2, negative 3, or is it 3z squared h3? So notice that's exactly all the. Ooh, I'm missing something. All right, this should be h1 squared. So this should be h1 squared. There you go. I fixed that. But anyway, notice that all the linear part in of the expansion of f of x plus h minus f of x, that cancels with the linear part that we thought we think is the derivative. And so in a sense, you're just left with higher order terms in terms of h. So all these cancel. All these go away. So now we can actually look at term by term. Well, I could be more efficient here, so I'm actually going to not do it term by term, but notice that these three terms all have a factor of h1. The last two terms here have a factor of h3. And you can be, there's more than one ways to do this one. Plus, and I'll do the other term, but this time factor out an h3. And I guess technically I should just be taking I can just take the absolute value of this and then apply some sort of squeeze. Okay, so let's just focus on the limit of the first term. Okay, so now I'm just going to consider the limit of the first term, or the absolute value, I guess. So let's just do this. Take the absolute value of the first term. Now we know by the this is equivalent to the magnitude of h1 divided by the magnitude of h times. Okay. Now, if you haven't, you've probably seen this already by now in this class, but you see that this factor should be less than 1, or less than or equal to 1, right? If you'd like, obviously, if you take any one component or any one term here, squared, you just add more non-negative quantities, the resulting thing should be at least as large. So no one term there is bigger than the sum of all three positive terms. And you take the square root of both sides, and then you get the magnitude of h1, and I could have used any h1, h2, or h3 to make the same argument. Okay, and then now if we divide, we'll get this factor is indeed is less than or equal to 1. And this is nothing mysterious. If you think in terms of like vector magnitudes, we're just saying that like a generalized triangle, right? Any one component, the magnitude of any one component of a vector cannot exceed the sum, or the magnitude of the total vector, right? So all I'm saying is that if h is a vector, then the magnitude of any one component cannot be greater than the magnitude of that vector. No one side of a right triangle is larger than the hypotenuse, right? All right, so nothing mysterious there. Okay, so now we replace this with something we know is bigger, namely 1. And then we apply squeeze, because obviously taking the absolute value, you get something non-negative. So we have that the absolute value of the thing we're interested in is less than this business. So taking the limit as the vector h goes to 0, vector position, whatever. By squeeze theorem, we see that for the limit on the left, of course, is the limit of a constant. On the right, you have, since vector h goes to 0, all the components of that vector have to go to 0. So evaluating this directly, we get 0. So we can see that our limit here is between two numbers, 0 and 0. It must be 0. So since the limit of the absolute value of that expression is 0, the expression itself must have a limit of 0. Right? And so the limit of the first term is just 0. And you make exactly the same argument for the second term, correct? You know that h3 divided by the magnitude of vector h is less than or equal to 1. So taking the absolute value, this is less than or equal to this divided by that is at most 1. So you're just left with the remaining thing. And now as we see that as vector h goes to 0, so does h3. So this will go to 0. And you can squeeze the second term at the limit to go to 0. All right, well, we proved it, right? We came up, we kind of theoretically knew that the derivative kind of looks like this function is differentiable, and that this derivative would be just the Jacobi matrix, and it acts on H by multiplying H, or H is like a column, or if you'd like, it's like the dot product of the gradient of F with H. And we used the limit definition to show that since this limit is 0, our function is differentiable at x. Okay, let's look at the chain rule example. So suppose f is some function that's differentiable, and it has two inputs and a single output. So let's just say that's a function from R2 to R. And suppose g is a function from R2 into R2. What we're going to do, hg, so let's call this, okay, I'm going to start this over. I'm going to say h is a function from R2 to R2. G is a function from R2 to R1. So you can think of this as taking vectors in R2. H will pick them up and return another vector in R2. And then G takes that result, will take that result. So we're going to be talking about composition and output a number. So in R1, just real numbers. And we're going to compose these two. We'll call it composition F. And I'll probably look at very specific. Maybe G is generic, I don't know. So G might be a function of U and V and return some number. Now H, we might make it specific. So H is going to be a function of, let's say, variables x and y, and then return two coordinates. And let's just keep it simple. So let's just say 2x minus y, x plus 3y. Now we're going to create a new function of x and y that is the composition of G and H. So we see that f is a function of x and y ultimately, but it's G, but evaluated h of xy, where h of xy returns a first coordinate 2x minus y, the second coordinate x plus 3y. So if you'd like, u is equal to 2x minus y, and v is equal to x plus 3y. So I can then, we can then reasonably ask for the derivative of function f with respect to x or y. So one way to do this is to say, well, I know that f is a function of, it's G composed with f, and G is a function of u and v. So you can use this kind of tree to see that G is a function of u and v, but u and v in turn are functions of x and y. So if I want to know the derivative of f with respect to x at a point, this is just a schema here, I see that I would have to go through G. To get to x, I would have to go through G, and then through u and x, right? And then likewise. And so that would be, you can think of this as you go along the branch, it tells you to differentiate G with respect to u, and then times derivative of u with respect to x, plus, right, the derivative of G with respect to v times the derivative of v with respect to x. Right, I don't know what G is, so the best I can write, and I can write that this is a, let's be more specific, this is the derivative of f with respect to x at a point. All right. Right, so this is the derivative of G with respect to u, but not at u, v, right, but rather h of x and y. and then times, and then the derivative of u with respect to x you can compute directly, it's just 2. Right, so the derivative of g with respect to v, since we don't know what g is, we can't really write anything except to say that we're going to evaluate this derivative at a u-v pair where u and v is given by h and xy. And then times the derivative of v with respect to x, we can compute directly, it's just 1. Okay, so we can do something similar for the derivative of f with respect to y. So this time we're going to differentiate g with respect to u, evaluated at h and x1. But then by chain rule, we have to differentiate multiply by the derivative of u with respect to x, y. So -1. And differentiate g with respect to v, and then derivative of v with respect to y, so 3. So I guess that's reasonable, right? But notice that we could have just done this with matrices as well. So if I write these partial derivatives here of f with respect to x and y as a row, then this would be, you can think of this as the derivative of g with respect to this matrix times 2, 1, and then -1, 3. You can confirm that's the same thing. So indeed, there is a formula in terms of matrices for chain rule. So if f is composition of h with g, or g with h, okay, then the derivative of f at a point is just the derivative of the, so to speak, outside function at h of x, and times the derivative matrix for h at x. So let's look at the sizes of these matrices to see that this makes sense. Okay, so we see that g is a function from R2 to R1. So the Jacobi matrix would be, our derivative in this case, yeah, would be a 1 by 2 matrix. Okay, so that would be this. Now, h is a function from R2 to R2. So its Jacobi matrix is going to be a 2 by 2 matrix. So that looks like that would be it. So let's see. This is 2 by 2. This is 2 by 1. Sorry, 1 by 2. Oh, this is, okay. So sorry, I'm going to start over. The derivative of h is a 2 by 2 matrix. So this should be this derivative of g. I accidentally erased that. At h of x is a 1 by 2 matrix. This is a 2 by 2 matrix. So multiplying those together, you get a 1 by 2 matrix, and that should be exactly the size of the Jacobi matrix for f. It's a 1 by 2 matrix. Okay. And so this would be the derivative of g. Well, you just take g and you differentiate it with respect to its coordinates, the derivative of g with respect to u and v. But we just remember we're going to evaluate this at h at xy, h of xy, and times, and then the derivative of h. So let's look at h again. Takes xy and returns some business here. So get the matrix, we take the first component and differentiate with respect to the first variable, and then the second variable. And take the second component and differentiate with respect to x and then y. So indeed, these match, right? With these being, yeah, that's exactly, yeah. Okay. Well, we can look at more examples next time. Maybe also talk about product rule, and maybe practice more with the chain rule. Thanks.